Good afternoon, everyone. This is our last session before Legendary Happy Hour. Woo! You guys gotta be more excited than that. Yeah, okay. I just want to quickly remind you, I'm also the social media chair. Like us on Facebook and Twitter and LinkedIn. I promise not to overload your feeds. It's just, hey, a reminder, EnerGIS is coming up. Hey, all the pictures are posted. All the videos are ready to be viewed. So it's nothing crazy, but go out there, like us, and have a look. So up next, we have Joseph Blickenderfer. Joe has been with Michael Baker International for over 20 years as a professional engineer. Over this time, he's contributed to and managed civil and environmental engineering projects across many service industries. He currently serves as Michael Baker's oil and gas design and permitting group manager. He provides senior technical and project oversight for the environmental design and permitting on all oil and gas pipeline, well pad, impoundment, compressor station, and any other site civil development. Joe has a strong background in federal, state, and local environmental permitting, engineering design, and construction. He also serves as the Marcellus Shale Coalition's co-chair of the planning and permitting work groups. So please welcome Joe.
Thank you. I'd also like to introduce Jared. Jared has some of the brains here behind the model that we're presenting today, and maybe I'll answer some more technical type questions as we go along. So, I'm sure many of you are involved in pipeline routing, a project that connects point A to point B. And what we find as we're progressing through a pipeline project is that the biggest contributor to schedule and financial delays in the project is rerouting. And rerouting really stems at the very beginning, the conceptual stage in the project, where we're trying to pull some of the available information together and come up with our initial routes for the pipeline. So, with that, we're always looking for ways in which we can help make that information more accurate. So a typical desktop analysis includes a lot of available information. It starts probably with like a Google Earth analysis, looking for roads, structures, populated areas, things like that that we would want to avoid. On the environmental side, we don't have that type of accurate information. So when we go to an HD stream information, and it's great as far as what's shown is fairly accurate, but it's very incomplete. We look at NWI mapping, show us wetlands, but again, not only is it incomplete, but it's very inaccurate. So when we're looking at putting a predictive model together for pipeline routing, those are areas we really like to look at to see how we can increase the accuracy of the model, maybe from other information sources. So again, we start with a conceptual desktop analysis, and from that, we've got partial stream information, partial wetland information, and very rarely do we do anything from a cultural resources or even a threatened and endangered species perspective. From that, our land agents go out, we get survey permission from landowners. We send our field crews out, they start to locate streams and wetlands, and surprise, surprise, the conceptual route that we had initially planned doesn't work. So we go look at some type of reroute. And with that, we're almost back to square one again with trying to find another conceptual route, renegotiating with landowners, and sending our field crews back out. So all this leads to schedule delays, more negotiation with landowners, and ultimately cost, and particularly, as you'll see throughout this entire presentation, another reroute. And really, that's the purpose of this model, is to avoid those as much as we possibly can. So our approach to this is to try to increase the accuracy of particularly the environmental models that we use in the desktop analysis. And to do that, we challenged the GIS group to interview a lot of the environmental professionals we have internally. So field biologists, asking them what kind of information do they look at, how do they use it, is there any ways we can increase their efficiency, either by providing them better data or by eliminating some of the repetitive type tasks that they do. We wanted it to be very modular, so if we're looking at, if we've got interest in looking at streams, we want to be able to look at those independently, but we also want to look at those with respect to maybe cultural resources or something else. So we need something that's very stackable in the end. And then we wanted to use GIS analysis just to make sure that what the information that we're providing is as accurate as possible. So from an environmental perspective, really what we're focusing on is streams, wetlands, cultural resources, and threatened and endangered species. So with those four things in mind, basically what we'll see here in the next number of slides is how we put modules together for each of those four components and combine them into a constraints map that ultimately, through some GIS analysis, provides us with a least cost path through all those constraints. So starting with streams, again, we look at NHD data. This is what you're looking at here is NHD data in blue with a pipeline route in red. And NHD data does a very good job of showing us the main branches of our stream channels. However, from an environmental perspective, that's only really half the game. We also need to know where the branches, the headwater streams, seeps, things like that occur, because that's another permit, or another type of permit that we would need to get as part of the project. So using LiDAR information and derivative information like contours and slopes, we're able to apply some GIS tools and do a much better job of delineating the water streams, things that we typically wouldn't find in a normal desktop analysis. But to a field biologist would say, well, that's very important. I need to make sure that I miss some of these complexes of headwater streams. And what you'll see in this figure is at the end of the dark blue lines, which is the NHD data, you'll see that network of headwater streams that we would need to miss in a routing project. And again, this is another illustration just on an aerial photograph of the blue, dark blue lines as NHD streams, the cyan color lines as lines that were picked up through our model. And from that, you can see if we were routing just from NHD streams, we would see probably 2 stream crossings in this corridor. Once the GIS analysis is provided, there's as many as 5 or 6 depending on the routing. So really the engine that drives this is the available aerial LiDAR data. When we look at the comparison to known streams, field verified streams, we find that we've got a very high correlation between the model and what we find in the field. So much so that we're fairly accurate, at least on the stream side from a conceptual analysis, of delaying some of our field survey work until we were sure that we've got a more firm route for our pipelines. So next module is wetlands. When we're in the field looking for wetlands, there's really 3 indicators for a wetland: hydrology, soil types, and vegetation. So with the information we have available to us, we can very quickly find hydrology based on the information that we just determined in our streams module, and so hydric soils based on the USGS information, and topographic features, again based on LiDAR for any low-lying areas or flat areas that we would expect to potentially find wetlands. Again, a picture here basically shows slope image where red's kind of the steeper slopes, green maybe low-lying flatter areas, and then combined with that is the USGS hydric soils mapping. So when overlaid and given the hydrology component of the earlier module, it gives us another very high likelihood area of wetland occurrence. And here's an example of that with the dark blue area being what was predicted based on the model, again on those 3 data layers. And what's shown there in hatch is the field delineated wetland. And again, you can see just how accurate that model ends up being. And ultimately what we're looking at from a stream and wetlands perspective is the combined composite streams and wetlands data layer. And this is important to combine based on the next few slides that we're going to see. So again, data needs, LiDAR is critical to provide us with the low-lying or flatter sloped areas. We also use the soils information that we get from the NRCS survey. Again, when we compare this to actual field data, the actual shapes may not be real accurate, but what we find is the potential for wetlands is very high. So if we're looking for areas that we would try to avoid because we are fairly certain that we will run into some type of aquatic resource, the accuracy of the models is superb. Added to that then is a cultural resource module, and when our archaeologists are looking to do some type of desktop analysis for potential ancient habitation, there's really a couple of things they look for, and the first is slope, just like we build our houses on flatter ground, so did the ancient people. Distance to water, you didn't want to carry water very far, so there'd have to be a water source nearby, and then they also have access to state SHPO office data that shows them where there's been other habitations found. So again, when we use the streams and wetlands model as the hydrology, the LiDAR information for the lower lying floodplain or even saddle areas, the ridge tops, and then combine that with distance to known habitation areas, it gives us again a picture of what the potential is for finding other ancient habitations. So data needs, again, there's a lot of the same type of information that we needed for the other modules. We basically pull our streams and wetlands layer in. Along with that, the state data layers to show us where those ancient habitations could occur. Again, as far as accuracy goes, a very high likelihood that the areas that meet the 3 criteria could potentially have some level of significant habitation. And the last module we have in the environmental section of this model is threatened and endangered species. And a lot of those data layers are available through the Fish and Wildlife Service or state agencies, DCNR, Pennsylvania Game Commission. But what we do here is find out what potential impacts we could have, whether it's plant species, and then look for habitat based on land cover use that particular plant thrives in. So we may have a T&E species hit on a project, but if we don't have habitat that would support that species, we can quickly roll those areas out. Again, giving us another data point for where we may want to try to route our pipelines. And again, very high correlation with existing data, because we're really just looking at land use at this point, and we've got known data from state and federal agencies telling us that we would expect to find this plant or animal species in that area. So we take these 3 modules, and it basically forms a constraints map for us with streams and wetlands, cultural resources, and threatened and endangered species to give us the composite predictive map. Again, just another view on an aerial photograph. But at this point, our work's really not done. We've done some of our homework now. Now we need to find basically the least path through all these different constraints in order to set our initial desktop alignment. And we do that by basically weighting a lot of the data that we've collected in the other modules. So for instance, if we have a project that's in an exceptional value watershed and we want to try to avoid wetlands and streams, more so than we would maybe a T&E species survey, then we would rate those data layers higher, so that whenever we apply our geotech processing, or our GIS processing, it will select that path of least resistance through all those different data sources. Again, here's a constraints map for a project we did in Cambria County. And on the left and on the right, I don't know if you can see it, but there is a black line through there that has an optimized route. And the thing to point out on this one, if you look at kind of the center of that figure, is very red. And red typically means an area we want to stay away from. That was the case on this project. That red area in the middle was an exceptional value watershed, and it also included a number of T&E species plants that we needed to avoid. And as part of this project, that area actually ended up being an HDD under the Conemaugh River and under the EV watershed and potential teeny species. So since this is modular, we can very easily add in other constraints that we might be concerned about right away. Land is always a problem, particularly here with midstream companies. So we can add parcel data for stay-off properties, things like that. Landslide prone areas, we can include landslide mapping, mining mapping, as well as construction for side hill lies, slopes, things like that. So ultimately, our composite predicted resource map can really be made up as many different data layers as we would want to analyze as part of that initial desktop review. So ultimately, what's the benefits to all this? And ultimately, the goal is to reduce reroutes. Again, reroutes are the #1 cause of schedule delays and additional costs to projects. It also gives us the ability to do some higher level analysis of properties that we may not have access to. So maybe Farmer John's a stay-off property, he wants nothing to do with the pipeline, but as we go through this analysis, we find out, well, heck, we can save a lot of money on this project if we can route through a piece of this project. So it gives us some idea of what the economy of that section of pipeline may be worth to us, so that in the end, even though we need to pay that particular landowner more, the project will still benefit from the results. And also, it's a great alternative analysis tool, because in the end, we've basically looked at an infinite number of alternatives that we can provide to the state and local agencies to show that we've done our homework, this is the best route, and it's more than likely going to be most permittable. So with that, any questions?
Have you thought about putting sort of like a predictive analytics module on it so that it will automatically, reroute itself to a more optimal route? Do you think it could do that?
Well, actually, since the basis of the analytical process is a truth table. So whenever we weight each of the individual data sources, it's automatically picking what the lowest cost analysis will be. So what will happen then is, once this map is produced, it'll go back to each of our our biologists, our cultural resource people, and they'll take a look at this just to see if there's anything that the model might have missed. At that point, there's ability for us to make some tweaks to that alignment, maybe straighten it. We don't want this path to be very jagged, lots of PIs. So maybe we'll straighten it out or something like that. But we can always dump that back into the model and make sure that whatever we come up with in the final is still close to the best solution.
Can you hard peg it to avoid areas, like once you know there's defined endangered species or whatever, but it just, it won't allow you to go there?
Yeah, we can. And again, it goes back to the weighting. We would basically rate that area much higher than the rest, so that the model automatically will avoid that area.
Default. Okay.
Right, by default.
Are your only deliverables the composite map and the data behind it?
It's the data behind it, the composite map, and ultimately the route is what's most important. And where we find that is most appropriate is in like a public setting. If we've got a township meeting, public meeting, we can present this and say, here's the data behind the model. There's very little human interaction at this point. So if neighbor Smith doesn't want the pipeline here, he's going to come up with 8,000 reasons why. We can say, look, we didn't look at anything other than the facts. Here's the data. Here's the route we came up with based on that data. So it's something that's very defendable at that point.
Have you ever had the need to turn that into something more substantial, like spreadsheets with initial crossing reports, anything like that?
No, but
someone could look at and
we haven't. But where it has helped us, and our clients, is on planning projects. So if they're trying to estimate project costs, they get a much more clear idea of maybe how many stream bores they may have, or how many wetland crossings they have. And something as a consultant that we always have a hard time dealing with, because it's a complete unknown. And there's a lot of effort goes into each one of those individual resource crossings. So if we have a better idea of what the number may be, we can provide better estimates in the beginning of the project.
Does the model account for various right-of-way widths?
It can. We would set an offset on that ultimate line for the proposed right-of-way widths. That's correct. So we would start with a much wider corridor, collect that data, and then narrow that down to what the optimal route would be. And then we can go back and instead of using the wide corridor analysis, we use something that's much smaller to kind of fit what that ultimate right-of-way would be.
Would it also adjust along the route? 50-foot right-of-way would be more suitable in one section, but 100-foot would work in another? Would it sort of fluctuate along the route?
Not without setting that.
Any experience or comments on the age, this 10-year-old Pennsylvania LiDAR? Have you found other routes where you had to go acquire new data?
Yeah, well, again, any model's only as good as the data that you put in. So right now, in Pennsylvania, we've got some older data. We are working with some other newer aerial LiDAR. Obviously, there's huge advantages to that, particularly when you're looking at gathering lines that are next to new well productions and other lines. There's always a lot of changes, particularly with the age of the Pennsylvania information now. We're continuously finding areas that have been changed since that's been done. So yeah, we have collected data for clients, not so much to run in this model, but just to update their mapping. So we would use the most accurate mapping we can find at the time.
Has there been an idea of integrating some multi-spectral photogrammetry into it and seeing that cover as well for the routes that you're choosing? A lot of the things is like there's rock outcrops and heavy tree cover in the routes that we choose. So.
Yeah, I mean, you could add that as just another module. It's just another land cover type, right? So because of the scalability, you could always find something else to factor into that least cost path, and you're just applying those values to the raster at that point. And the rankings, we start at 1 to 4, I think, in our process. And you could go as high as you want to, just to indicate those really stay away from areas or to avoid that tree cover.
Anyone else? Well, I'm glad we got to bring Jared into the conversation.
I'll make a plug too. Your question about extracting for spreadsheets or anything like that. There's a riveting discussion tomorrow at 10:30 about using FME for extracting that type of statistical data. So
I was going to ask if is it scripted in Python or is there an FME piece to it?
there's no FME piece to this. It's mostly Python and modeled.
Once you have all your data kind of put together, I guess it probably depends on how long your proposed pipeline. What's your runtime on this? Once you kind of get it all compiled,
Once it's compiled, it's quick as the model will run, which is pretty instantaneous. What could potentially take time is the amount of the type of data that we have. If we have to do some digitization or something like that, then obviously that's going to add to the actual time that we need to set the model up. If we've got a lot of data available to us, it's as fast as we can download that piece of data that we need to put into the model for analyzing.
And there's a lot of manual interaction still too to reclassify that raster data to get it into the model. So the actual click run to end time for that segment isn't going to be very long, but you have a lot of legwork in there to prep the data to get it in.